Hello, my name is Nicholas Pachek.
My name is Daniel Pasikoff, and
Yes.
we are doing home audio system.
Indeed. So a little bit of background on the home audio system. I guess it's kind of trivial. It's a home audio system.
All right, so the presentation structure, we're going to start off with the higher level design, then we're going to get into the filter network, basically talk about why we chose the different frequencies, go over the design process, and from there talk about kind of what we've done so far in terms of the design, simulation, testing, and the results of what we have.
So this is our high level design. Idea being, this is the main portion of the project right here, being we have three filters, right? We have a bass filter, a mids filter, and a treble filter, in addition to amplifiers at the ends of each filter so that you can boost certain frequencies as opposed to other frequencies. All of those go into a summing amplifier, and then obviously the next portion of this project would be to put that into a Class D amplifier. At the output we have an impedance matching transformer, that way we can use a multitude of different speakers, that way we have maximum power transfer across them. And then all of these things that are kind of circled in blue are kind of our stretch goals here. So right here we have a super heterodyne receiver. So idea being this could be the input for a radio, some Bluetooth audio, and then the phone audio. So this is what we'll actually be using, is the phone audio. And then you see right here we also have a linear frequency modulation, which will allow us to perform a sweep of frequencies into the different filters and see how they respond. At the outputs of each filters, we have the microcontroller measuring each voltage, which will then be displayed on the OLED display. And we'll talk about the VBTs later on.
All right, so we've got the filter network. Next. All right, so we need to split this up into three different frequency ranges. You got a bass, a mid, a treble. So for the bass filter, it needs to be audible, but you don't want too much of that lower end boom. You want to get a bit of punch. So if you have a bad speaker system, you can still hear the change in bass. If you were to eliminate this frequency range, it would sound very tinny and it just wouldn't be good. With the mid range, that's going to be the meat of the frequency range. You're going to hear everything in there. If you take that out, you've got basically nothing. So mids are going to be the most important, around 600 hertz range. The treble frequencies are going to be that higher end sparkle. If you remove that, you're not going to hear any elevating sounds. It's all going to be boom boom, like a bit of punch, but you're not going to really get that sparkle. So those three frequency ranges, we saw a website that verified the range for each, and as well on an digital audio workstation, verifying the frequency range there. So those are the selected ones.
So I guess when you kind of come across this problem, like Daniel was mentioning, we have all these frequency partitions that we've chosen, but there's so many different ways to approach this, right? So their design approach for every single filter that when we're designing something is, okay, we choose which frequency and bandwidth we're gonna, actually try to design around. So we set those, and we pick a filter topology. We went through so many filter topologies, Sallen key topology, multiple feedback topology. We even touched on some state variable topology, which we'll get into later. Then we derive the transfer function for each of these topologies, and then create our own analog filter wizard for these, which is done in MATLAB, which we'll also demonstrate later. This analog filter wizard is pretty interactive. I think it's pretty cool. It allows us to compute the component values. Right after that, we go straight to the simulation. We're going to simulate it, make sure everything's working well, make sure that our actual component values are aligning to the correct frequencies that we want them to align to. And then we hand it over to Danny, and we build and test the circuit. And we confirm the response, and we just do this for all of the frequencies, right? For all the frequency partitions. So we can hit it again. So this is our preliminary designs.
So this is the first Chevy Chase multiple feedback bandpass filter. Basically the pros, it's got really steep cutoffs, so you can have a lot of accuracy with that. You're gonna have good frequency control. Difficult thing, it's really hard to implement. You can see tons of stuff there, and it's going to be out of phase. You're going to have a lot of phasing issues that you're going to have to work on later.
So idea being with this one as well, it's 10th order, right? Like Danny was mentioning. So look how long this is, right? This entire thing takes 2 quad op amps, and it's a pain in the butt to build. So our next design that we kind of went upon was the VBT, the variable bandpass tuner. This is my personal favorite design. I've spent 30 hours on this design. and it's based off of state variable topology. So the idea being we have a summing amplifier here and two RC integrators right here. RC integrators add a pole to the transfer function. So a pole in the transfer function is a 0 in the denominator of the transfer function. That just basically means that's where you're going to see your actual attenuation occur at the minus 3 dB cutoff point. And then we have an op-amp feedback loop. So idea being with this topology, you get a high-pass output, a band-pass output, and a low-pass output. And we have different feedbacks, so the low-pass output feedbacks into the summing amplifier, in addition to the band-pass output being amplified, then going back into the summing amplifier again. Now, with all these feedbacks that are occurring, and you're having these three filters in parallel, the idea being you can get a lot of cross communication. Different filters will have different currents going into other filters. So we added a buffer at the beginning to make sure that everything's isolated and to reduce reflection coefficients. So this is the demonstrated variable bandwidth and demonstrated variable center frequency, meaning with one filter, we can achieve any center frequency that we want with any bandwidth that we want. So I guess the advantages to that are, well, it's the design process is a lot easier. And if you have like a really certain frequency inside of your music that just sounds like crap, you can make that a notch filter and cancel all that out. So this was one of our preliminary designs. These are all VBTs. The response was good, but once we tried to implement a VBT specifically, it's very difficult to do. So yeah. So this is our current design. Right here we have. So this right here is a second order Buttersworth multiple feedback topology, and so is this. And when you cascade them together, you get 4 poles, which is fourth order. The Buttersworth part just means how the coefficients are determined. So the idea being a Buttersworth filter has more of a rounded peak compared to like a Chebyshev filter, which we originally had, which has low passband attenuation, in addition to a flat frequency passband response. So right here we have those two cascaded, in addition to a non-inverting amplifier right here. The advantages to this are that each 2 poles inside of a transfer function give a 90-degree phase shift. So if you have 4 poles in a transfer function, you're going to get a 180-degree phase shift, which basically means a 180-degree phase shift. Well, that is in phase, so you don't have to worry about any phase compensation, which is better for us. It's fourth order, so we're going to have we're going to have the ability to control the frequencies better. That way, we're going to have a really steep cutoff. Cons are it's not as cool as the VBT, right? So.
All right, so for the derivation, basically setting up KCL, we've all done that in signals very recently. So start with KCL, then solve for V out over V in, very similar to the intro lab, and get the transfer function equation from there.
Oh, do you want to play this video? It's a video. Let's see. Yeah. So this is our analog filter design wizard. Right here is some of the code for it. Yeah, cool.
Let's go.
So idea being we're changing the center frequency, and as you can see, as we're changing the center frequency, the resistor values corresponding to that is also changing, and we can see the plots moving to the side as the center frequency is changing, blah, blah, blah. This is a slow animation, so I'll speed it up a little bit here, if I can. Well, it's already over, so. But yeah, as you can see, as I'm sweeping the center frequency, it's also moving, so that's our wizard there. So this is just the cascadation. So as Danny was talking about, we derive the transfer function for each individual filter, and then we just cascade them together by convolving them together. And then we get a fourth order transfer function, right? So as you see, we have S squared here, which means a second order, and then we have a squared term here, which means it's going to be fourth order once you end up simplifying it down.
Just to note, one thing off of Nicholas, what he was saying, the order is determined by the amount of capacitors in the circuit.
Yes. So this is kind of not our final design, but our current design that we're on. So as we previously mentioned, fourth orders, each one is a fourth order bandpass filter of the Buttersworth topology, or Buttersworth coefficient type with the multiple feedback topology rather. And then the total transfer function down here, granted that each one is in parallel, so we're adding them together, so each one's still fourth order, in addition to applying the non-inverting summing amplifier right here, which is derived here.
All right, so now we have the physical circuit. As related to the last one, we got the bass, mids, trebles. We're using an LM324N quad op amp. So you've got 4 quad op amps there. And this bottom half is the actual equalizer part, the top half is used for the subbing amplifier. All right, so now input-output specs. The input to the circuit is going to be a computer headphone output. This is going to be estimated around 1.09 volts. Now, when we calculated in LT Spiced the output of that simulation, we got 5.9 volts. Now, that's a bit high. We've got to adapt that to get that a bit lower so we don't oversaturate any of the op amps. But that's where we're at for now.
So idea being, kind of touching on the last slide as well, just once we go to do our final implementation, this is a simple voltage divider you throw in there. So this is our simulation for the 3 filters, as you can verify that they all hit the frequencies that we specifically hit, being 150, 600, and then 1.8K, and along with the correct bandwidths, as you see.
One quick thing to note, can you go back? Yeah. One quick thing to note about the frequency spectrum here, as you increase, the differences become much larger. So, or no, when you're on the lower end, the differences are much larger. So 50 hertz down around the 100 hertz range, or a 50 hertz difference around 100 hertz is much, much larger than 50 hertz around 10K. So it's not proportional there, just to keep that in mind.
Yeah. Logarithmic. So this is the total response. We have another video here if you don't mind playing that. So idea being, this is our total response when we actually sum it all. Now we do have a notch here, but that can be fixed just by our boost value. So here we have a simulation of all the combinations that we could possibly have with different R boost values. So as you see, the notch goes away when the bass is amplified. Hit it.
All right, so now we tested the bass filter in LT Spice. Verifies perfect. You can see the phase shift, 180 degrees perfect, and you can see that boost, that peak right there, which is going to be the filter.
You meant to say waveforms, not T-Spice.
Oh, waveforms. Pardon me. Waveforms.
Yeah.
Same exact thing with the mids. You can see the exact same behavior here. Except on this one, you can see the peak is a bit higher than the last one. So we need to equalize the outputs, that they're all relative. We haven't done that yet, but that's the next step moving forward. Next. And now you can see the high pass filter, or not high pass, the band pass filter on the treble side. And it's the exact same behavior with the phase shift, 180 degrees, and the bandwidth. As you can see here, the bandwidth looks much larger. That's just due to the increased spectrum. Next. And here's the total response of them working all together in unison. You can see, again, what I touched on a bit earlier. The levels are not equalized. Moving forward, that's the first thing to implement. But as you can see, the behavior is all working as should.
So one thing on this one as well, the reason why the levels are not equalized is because every single filter uses different resistors, right? Which means every single filter is going to have a different power dissipation, as we showed in the previous slides. So as you see, these two filters are equalized because they're in similar frequency spans and they have similar bandwidths, while this filter still is a little bit lower, as when we were testing at the moment. That's a simple fix. So here's our graphic equalizer portion. Here's another video we want to play. So this is our simulation for the graphic equalizer. Idea being we have our bass filter, mid filter, and treble filter with the different colors right here in the legend. So as we increase the bass filter, as we see, the bass filter also increases. I'll lower it. And then as we increase the mids filter, we see the mid filter increases, with the blue being the total transfer function response. And as we increase the treble filter increases. Here's some of the code for it. I really like the MATLAB live simulations like this, but yeah. Here's some of the code for it. This is just for the milestone 2 portion, very basic code, just showing our name. Idea being, once we're actually going to implement this, we want to have a much better system. So the things that we're considering implementing is, as you look back to the high-level design, having the Arduino being able to give select bits for the muxes that are selecting the inputs, in addition to being able to send in the linear frequency modulation to be able to have a network analysis of the whole entire thing. And then for our stretch goals, being able to digitally control the parameters on the variable bandpass tuner. And then all of this is going to be displayed on the display. Some sources, and then
that's
it
it
again, and then that's just our appendix, so some of the different functions. So, is there any questions?
Questions?
Okay, you already took like a lot of time, okay?
Oh, I'm
So
sorry.
we don't have any time.
Okay.
Thank you.
Oh my gosh, that was